a projectile is traveling at 0.07 kilometers per second for 9 seconds. The distance can be calculated using the formula d is equal to r times t. Distance is equal to rate times time, which we've seen before. What would be the most reasonable unit for the distance? So let's just think about this a little bit. We can say that distance is going to be equal to the rate, and they've written the rate in kind of a strange way, but I'll just write it that way for now. Distance is equal to 0.07. Let me write this. I'll write kilometers in orange. Kilometers in orange, and I'll write seconds in blue. So 0.07 kilometers per second, that's its rate, for 9 seconds. So times, and let me do this in a new color, times, I've already used, let's see, I haven't used pink yet, for 9 seconds. So times 9 seconds, and I'm going to write seconds in blue. So what would this give us? Well, we can, as we've seen before, we can multiply the numeric parts, 0.07 times 9. That is going to give us 0.07 times 9 is, let's see, 7 times 9 is 63. So this is 7 hundredths, so it's going to be 63 hundredths. So it's going to be 0.63. It's going to be 63 hundredths. And then our units, we have a second in the numerator being divided. We're not really dividing the second by seconds, but when we're thinking about how the dimensional analysis works out, a second in the numerator, a second in the denominator, you can cancel them as you would a variable, although obviously these aren't traditional variables. These are units, but you can operate on them in a very similar way. And what are we left with? Well, we are left with kilometers. We are left with kilometers right over here. Now, is this reasonable? Is it reasonable to call this 0.63 kilometers? Well, kind of. I wouldn't say that this is the best way to express it. I'd add, since we're looking at a essentially fraction of a kilometer, I'd rather describe it in terms of a unit that is smaller than a kilometer. So let's say meters. And actually, all of these are smaller than kilometers. But let's think about what it would look like in terms of these things right over here. So let's first convert this into meters. So we want to get rid of the kilometers. So let's put a kilometer in the denominator. So 1 kilometer in the denominator. And let's put a meter in the numerator. So how many meters is equal to 1 kilometer? Well, 1,000. 1,000 meters is equal to a kilometer. So kilometers cancel, and we're left with 0.63 times 1,000 divided by 1, if you want to care about that, meters. Well, what's that going to be? That's going to be 630. So if you take the product of that and that, you get the numeric part. You get 630, and the units that you're left with are meters. And it's important to always say, does that make sense? Because sometimes, like, hey, do I multiply or divide? And obviously, hopefully, the dimensional analysis helps clarify that a little bit. But if you're expressing something in kilometers and you're going to go to meters, it's going to be 1,000 times as many meters as what we see right over here. So this is 630 meters, which actually seems like a reasonable way to actually describe a distance. But let's think about if we wanted to do as centimeters, just to show that it gets a little bit more ridiculous. So if you want to describe 630 meters in terms of centimeters, well, once again, we want the meter here in the numerator to cancel with a meter in the denominator. And we want centimeters now. We want centimeters. So how many centimeters equal a meter? Well, 100. So this is going to be, meters cancel out. 630 times 100 is going to be 630 with 2 more zeros. 2 more zeros. So it's going to be 63,000 centimeters. 63,000 centimeters. Now we're starting to get to numbers that are a little bit harder to visualize. 63,000 centimeters. I really want to describe this in meters. So I definitely wouldn't go for centimeters. And millimeters is even worse. You have 10 millimeters per centimeter. You're going to get to 630,000 millimeters. So that's even stranger. So I would definitely go with the meters.